Okay, thank you. Yes, welcome everyone to this webinar on NeuroSymbolic AI and how it is used in HumAIne. So I'm Spyros Theodoropoulos. I'm a researcher at the University of Piraeus Research Center, and I will be showing a bit the technical part of the task, the component we have developed, and a short demo. So a few words about HumAIne. So the goal of HumAIne is the creation of a unified platform for novel AI paradigms that also feature advanced and trusted human-AI collaboration. The platform currently has 4 AI paradigms: active learning, swarm learning, neurosymbolic learning, and explainable AI. The aim is to apply these paradigms in dynamic real-world environments across also different industrial sectors. So we have smart ticketing, healthcare, energy, and so on. In this specific presentation, we will be focusing on neurosymbolic learning and its application to healthcare. So what is neurosymbolic AI? There are many definitions and many taxonomies. But as you might expect, it's a combination of neural, so data-driven AI, usually via neural networks, and symbolic AI, so that, let's say, more traditional AI that has to do with symbolic rules, with knowledge graphs, with ontologies. Another way, perhaps, to think about it is for those familiar with Kahneman's best-selling Thinking Fast and Slow book, is that it's a combination, an attempt to combine system one, which is more perceptual, more intuitive, and works with vast amounts of raw, unstructured data, and system two, which is more deliberate and has to do more with analogy, reasoning, and long-term planning. What do we aim to gain from this combination? One thing is context awareness. So symbolic rules, which are very, very specific, can gain a bit of context from the data-driven learning. But also the data-driven learning can become more robust, learn with less data, and also become more explainable via the addition of the symbolic rules. Again, as I said, there are many taxonomies, but to simplify matters, we can very roughly say there could be 2 categories of neurosymbolic AI. One is to ultimately perform a symbolic reasoning task, which is helped by neural networks. For example, some predicate might have to do with images and could be learned from neural data, but our ultimate from the data, from raw data, but our ultimate aim is to complete a symbolic reasoning task. And then the second is the reasoning for learning task, where we have traditional machine learning as you know it, from data that goes into the neural network. But we want to improve it because, let's say, we have some specific domain knowledge. And so the symbolic reasoning can now be added to constrain the neural network. There are various technologies, especially for the second category, which is perhaps more applicable to most problems, more flexible, more easily applicable to most problems. One is logic tensor networks, which attempts to add fuzzy rules to the loss function of the network. Then there is the semantic probabilistic layer, which adds an extra layer on top of the network, which can also guarantee strict satisfaction for the rules. The LTNs do not, the fuzzy rules of the LTNs do not guarantee that. And there are also other techniques such as signal temporal logic networks, which can be used for time series. And there is also a few interesting tools in IBM's toolkit, more specifically neural unification for logic reasoning over language, which, for example, could be used for fact-checking chatbot advice. So a few interesting applications there. What we mostly use in the project is logic tensor networks because we deem this to be the most flexible approach. And in real life, we have, for example, noisy data sets, and formulating like very, very strict rules is perhaps also not always possible or advisable. So we want to get like an intermediate combination where, okay, we have the data-driven learning and we have some fuzzy rules that are used to guide the training, but are not enforced strictly. And we see here schematically how this works. So the rules become part of the constraint laws. One can also use additional information from external classifiers and combine them with the rules. And thus provide like an enhanced form of learning. Now a little bit about how this works as a whole in HumAIne. Let's say an important purpose of HumAIne is to provide systems that are human-centric and that figure human-AI interaction and enhance AI via human interaction. In our case, we want to develop a component that can be used and work synergistically with two types of users. One is the non-technical domain expert, another is the machine learning engineer. For now, let's focus a little bit more on the non-technical domain expert. This user can provide their domain knowledge via a UI we created in a special and intuitive way. For example, they can define rules in natural language. And these rules are then used by the NSAI algorithm to train a model. However, first they have to be converted, and that's why we have this semantic interoperability component that uses an LLM in the backend and tries to convert these rules, to encode these rules into a format that is suitable for the NSAI algorithm so that can embed them to the loss function. So it extracts, let's say, structured data from the unstructured natural language, then embeds the rules to the loss function of the neural network, and proceeds with the training. In the end, our output is a trained model that has the domain knowledge defined by the non-technical domain expert. Another functionality we provide is some explainability functionality. So the user can define rules, train the model, see how it performs in certain instances, see the explanations, and see, okay, is the model, do the predictions adhere to my domain knowledge? Do they make sense more generally? And then they can decide whether they want to run a new iteration, perhaps tweak something in the rules they provided, or whether they can accept the model and save it so that downstream consumers, users of the HumAIne platform, can make use of it in their applications. The machine learning engineer is there more to take care of tasks like maintenance, debugging, and perhaps tweaking of the algorithm. Now let's see a short demo of this component. The demo is quite long. I will skip through some parts to show what is most important only. The UI we are going to show you now is running in the backend of the HumAIne platform and is supposed to be used by a non-technical domain expert, for example, a healthcare provider that does not want to develop their own model, but that has some idea of the domain and can therefore provide rules in a format that we will see that can influence the model behavior through the use of NeuroSymbolic AI algorithms. So let's go straight ahead and look at the UI. So here are some options. Okay, I will skip through these options and go straight to the training process. I can upload the dataset either through a CSV or a MinIO path. First, let's do a full run through the CSV. We will use the breast cancer Wisconsin dataset, which is a relatively simple healthcare dataset. Here we should mention that the component is independent of datasets. However, it is designed to handle tabular datasets, as you see here, with integer with numeric columns. And also the diagnosis should be a single column. In this case, it's a binary diagnosis, a malignant or benign, or a malignant or benign. So we can choose several columns to drop. and we can also choose which is the target column of the ones provided by the file. And this will load the data and create training and test sets for the model to be trained and evaluated. And these are determined by the random seed we choose here. So now the train and test sets have been loaded. The next step is to define some predicates. These predicates should not be random. They should refer to the columns of the dataset that we have uploaded. And because we actually, in the next step, we try to parse the rules from natural language text using LLMs, it's good that the names are meaningful and also relate to the column names. Okay, so here we define some dummy predicates. This is just an example. The next predicate that we will add, again, the value is 5, and the comparator is less of generation. But this generated code is mostly. And this shows the predicates that we have defined. This general module works via code generation. We saw this in the UI only for debugging purposes. It will be removed in more mature versions of the component. But you can see here that we have predicates, they refer to columns, and they say, for example, this column, if it's greater than some value, this predicate is true, something like that. And then we go to the rules definition. Find rules that are based on these predicates. So let me input directly a rule here, which says if the clump thickness is high, but my dose is low, then the tumor is malignant. So you can see that the predicates that we defined are mentioned in the rule. However, the rule does not follow any strict syntax, so it can be a natural language sentence, which we can add, and then select and save. And this save functionality will now ask the LLM to turn this rule into a structured format that can be used by our algorithm. The reason we provide this interface is obviously that non-technical domain expert, it will be difficult for them to write the rules in the format that the algorithm expects. And so we provide this natural language interface so that it's easier and usable for them. Okay, so this shows now that the rules have been processed. Here we again show the generated code that is for debugging purposes. Let's now train the models and see what the performance is. And here we have the. So this was a sample training run with a rule that is non-meaningful, and as you can see, the performance between MLP, so the simple neural network, and LTN is exactly the same because like the rule does not really affect what happens. After a little bit, we define some in the same dataset. We define some predicates, as you can see, that are more meaningful. And let's see what happens with those. Normal nucleoli and low mitosis. We can now use these simple predicates in rules, as we saw before. So let me add the rules. The first one says that if the patient's clump thickness is high and the cell shapes are highly uniform, then the tumor is malignant. Then we have another rule for malignant using some different predicates. And then we have a third rule, which says which predicates need to be satisfied in order for the tumor to be benign. Notice here, for example, that we say the tumor is benign. However, the benign concept does not exist in our dataset. Yet still, the underlying LLM manages to infer that it should predict not malignant in this case. So now we select all the rules. We need to select the rules to make sure they are applied. For example, if we might want to experiment with different sets of rules, we might unselect one of them. And then we save the rules so that they are translated in the machine readable format expected by the algorithm. Okay, so now we see that the rules have been translated and we train the models using the rules. Let's see the results of the training. Okay, and here I will go very quickly. So now the rules produced an improvement. Generally, the score here was good already, so it's difficult to produce something even better. The difference is not much. Let me also say that the dataset is imbalanced and the rules do not cover every instance. That's why you see so low score for the rules. And let me skip now a bit to the explainability screen. Again, I will go through this very quickly. So we select the patient ID, or let me actually play the video for
So we
a bit.
select our patient IDs from the test set. These are more to see how the model behaves on certain instances. For example, let's choose a patient with a malignant ID. We have here number 9 as to label 1. We can see their features here, and we can get the predictions of its algorithm.
Let me skip a bit. So we get like the predictions of its algorithms, as we said, and we get some feature importance scores from SAP. If you can see here, some of the predicates we defined in the rules usually come high up, depending on how the instance also satisfies the rules. And in the end, we also provide this natural language summary. So this is done through an LLM interag that gets fed with the feature importance scores and the rules satisfied by this instance. And depending on the domain knowledge used in the RAG database, it tries to create a meaningful explanation for the domain expert in case the above diagrams are not clear to them. And let me now finally go very quickly to using the ISP dataset. So this is loaded from MinIO.
Essentially, to predict episodes of hyperglycemia. So we enter here the path where the dataset is saved in MinIO. And we load the dataset. And we select this ID column to draw, as well as this whole hypoglycemia column, which is the target column that we do not want to predict. We want to predict hyperglycemia. So the sets of data have been loaded. Also, so that I don't forget, we need a few more training epochs for the diabetes dataset. So we set training epochs to 1000.
And then we define some predicates, some simple predicates like we did before. One thing that is new here is that we can define also some composite predicates that make use of the simple predicates. Let's show this bit.
Composite predicates, which are predicates that are combinations of the simpler predicates we have defined. The reason we define them are so that we can make the expression of rules a little easier. For example, we might want to reuse a meaningful composite predicate many times in our rules. So let's see a bit how this functionality works. So the first is the predicate exercise is enough. We can see here, we can select from the predicates we defined in the previous step. So we select walks enough and gets intense exercise. We can select here whether to put a not in front of it. And we can use a binary operator. In this case, we will use OR. Okay, here we can see all the predicates again. Now we can see we have some composite predicates, exercise is enough. And then we add another one called healthy lifestyle.
Okay, this is similar to before. Let's go now a bit to the rules.
So then we will define two rules here. The first is if the patient gets enough exercise, has low blood glucose, and a healthy lifestyle, then the probability of hyperglycemia is low.
As you can see here, again, the rule format doesn't have to be exactly the same. So we say low probability of hyperglycemia. The logic behind this will understand where it fits better. So to which label it fits, hyperglycemia or no hyperglycemia. Let's keep here. We add those rules, we train the models, and we see, for example, in this use case, there is, in this case, a big improvement through the combination of rules and MLP. And in the explanations, another thing to note is that LTN predictions are usually somewhere between the MLP and the rules. especially for instances that are covered by the rules. So this shows it's kind of an average here. And also we can see that in the feature importance scores, some of the columns we use to define predicates, normalized glucose, intensity goal, sleep goal, very often come out towards the top. That's it for the demo. So to wrap this up, this diagram shows a bit how we want to integrate with an external downstream client. It's very similar to the diagram we saw previously. The only thing I want to focus on is that, for example, if the external client, let's say Healthentia in this case, they can upload a dataset to MinIO. So the communication with external clients happens through MinIO and these messaging channels, which are probably going to be RabbitMQ in our case. So Healthentia uploads a dataset in the bucket. This is accessible by the UI we just showed, so a healthcare provider can go in, put in the rules, train the model as many times as they want. And then at the end of this model training process, the expert can say whether they can accept or reject the model, whether the model is good enough to their judgment. And if they accept, we send a message to the message bus. We save the model to a bucket in MinIO, a specific bucket, and we send a message in the messaging channel that says, okay, to the external consumer, you can find the model here, load it, and use it as you want. In the Healthentia case, as we will see later, it's for issuing patient's recommendation and advice. And in terms of next steps, how we will continue work on this, we want to make this component more generalizable. So we want to expand to different modalities, for example, handle images, handle text, cover cases as X-ray image diagnosis, or email spam classification, or whatever other thing people want. And the component is already kind of generalizable in the sense that it can work on any domain defined by the domain expert. And we also want to enhance it from the ML engineer perspective, so that an ML engineer can provide their algorithm, and we can automatically embed their algorithm into this UI, so that they can quickly create a tailored solution for their use case. That's all from my side. Thank you very much. We can go to the next speaker.
Okay, so I feel that we maybe should have gone first. Kind of, this is the more abstract thinking of what we had as a challenge, and the use case, I mean, the diabetes. So we got straight into the technical stuff. So I'll go a step behind and start from the beginning. So what we face, the chronic diseases account for 80% of the deaths worldwide, and it's a challenge to understand how we can support these patients to self-manage at their home setting. So we want to help the clinicians offer this digital healthcare at home, and we want to use the expertise of these clinicians with AI together into a hybrid intelligence system. So this project was an opportunity to do neurosymbolic learning, combining these data-driven insights from both systems. So that's the overall background. So we went off to create these innovative tools to collaborate between them, collecting the data from Healthentia, from our app and the backend, the expertise through, again, partially our portal, but also the MinIO, like Spyros shown just before, and of course the technology that is all integrated into the HumAIne platform for NeuroSymbolic AI learning. So the goal is here to provide at the end to the patient personalized remote care advice based on the progress and the data we collect from them, from their daily life. This technology is for both patients and for healthcare professionals. Patients will receive an app and a wearable and coaching, as I mentioned, advice, AI-driven advice on their phone. And the healthcare professionals, we have a web-based dashboard in Healthentia, patient data visualization. I'll show you some screens at the end. And all these decision tools and the model helping to explain why these factors are important and what type of advice we need to give. So again, we broke down the requirements into these three categories. Of course, the ML engineers are also a stakeholder, and they've helped to create these models in order for the AI tools to consume the data and give them advice. So I think more or less the metrics are here to combine the expertise and to validate these models towards if the advice was correct and if it has taken into account the insights of the data correctly. We're aiming to improve the quality of life of the patients, help them engage with their self-care, and for the healthcare professionals to be able to get the help. As we can see in the lifestyle is becoming more and more, let's say, a treatment, a prescription, but without a recipe, and without the details of how to go about it. So it's important to get their expertise into the system so that there's an automated way of helping the patients cope with the lifestyle changes that they need to do. So the AI generates the advice recommendations, but always the healthcare professional has to make the final decision. And again, in the decision making, we have a synergistic approach, a partnership between the expertise of the clinician and the outcomes of this NeuroSymbolic AI. Again, the aim was to develop, validate, and provide these tools in order to select the most appropriate advice. And this is given based on the experts AI collaboration, as I mentioned before. So imagine a patient at the comfort of their home. They receive coaching advice, lessons, articles related to what their most critical need is in order to achieve a better outcome. In this case, what we've used was the hyperglycemia. So we wanted to predict hyperglycemia and what the patients could do in order to avoid that event. So the advice is given through this coach mechanism, and it is selected by a model that offers these predictions. And it analyzes the decision in terms of the importance of the different attributes. We'll see all the factors, these attributes in a second. And we select the most important attributes to coach for or against. Again, the components are the app, the portal, and the AI modules. We referred to it before. So looking closely to the attributes of the dataset, we have a few fields related to demographics, like sex, gender, sex, age, and certain living status or educational as well level. That also helps into how you want to approach the coaching to the individual. Physical activity, daily step count, active minutes measurements from the tracker, sleep, the duration from the tracker again, blood glucose. These are daily measurements, giving us a trend, taken in specific before and after events, like before and after the meal, or before sleep, or after wake up, after fasted wake up. These all measurements are expected to spread across these different phases during the week. This is also called like a control week, that we spread these measurements so to have an overview of and get the right trend. Regarding weight, we have sporadic self-reports and requesting at least once per week weight measurement. Nutrition, we have self-reports, but mostly using the Mediterranean score, which has a qualitative and quantitative aspect of the nutritional levels of the individuals. We ask them about their knowledge of the disease through a license questionnaire called the DKQ24. Diabetes knowledge questionnaire. It's related to 24 questions, and it asks you, it understands whether the patient is aware of the, let's say, the mechanics of the disease. Again, coping with the disease is also another very interesting questionnaire related to diabetes, and how people manage their disease. And paid is another license questionnaire related to negative emotions, related to the management of diabetes. And GAD-7 and PHQ-9, they're very well-known license questionnaires regarding anxiety and depression. Maybe one would say they're too much. Perhaps paid is also enough, getting the anxiety related to the disease. But getting a more holistic view on the mental well-being of the patient is also important. The quality of life using the EQ5D5L questionnaire, which splits the main 5 levels of 5 dimensions of quality of life, like mobility and again, anxiety and usual care, daily care, and independent activities. And last but most importantly, the hemoglobin, which is a clinical measurement taken at the start and at the end of the study. Ideally, we would have wanted to check the hemoglobin, but it's very small endpoint, so we wanted to create a richer data set with multiple feature vectors in order to be able to help the model address all these different attributes. So the concept, again, the paradigm is how to create a new model that learns with the combination of these collected data and the HCP expertise. We use in both settings this data set. And as I mentioned, these are split or separated in feature vectors, and the knowledge of the expertise are formatted into the system that Spyros showed before. And we are considering, and we see that we can get a better model performance using these rules, as it was shown in the video before. So we have worked into two workflows, an online and an offline learning, in order to select dialogues. Very briefly, this is the offline learning, that data sets of 2 weeks were coming in the system to check, for the model to learn and to see whether it can correctly predict the hyperglycemia. This is the model report at the end. So the whole process is that the healthcare professionals' expertise is setting goals in our system. It also gives rules in the other platform. The data are processed into feature vectors, as we mentioned, and temporarily stored in the vectors database. The sub-process of neurosymbolic learning trains this model on a training set, together with the expert knowledge, and the performance of the model is validated until the machine learning engineer is satisfied with the validation performance. And once this is assessed, the resulting model is stored in the database. And then this is the online learning, where this model is consumed almost in real time, in order to select, to receive the attributes, which areas we need to focus on in order to get the correct dialogue to send to the patient. And then at the end, the patient receives the message. So these are two parallel sub-processes. We've seen early results that indicate an enhanced model performance using this method. We have balanced accuracies of 61% for the model learned on data only, while 67.5% using the model. It's still very low, but the patient volume was small, so the data set was a small data set. But we still had 10% higher balance in accuracy. So I could show you more detail. I have a video demo, but I think we're out of time. So through Healthentia, a partial expertise of the HCP is setting the goals for the patient. So they go into each patient record page and define where they want to aim the patient in intensity, minutes, weight, sleep duration, and steps. And then the rules are inserted in the other system, like we showed before. These are the BI dashboards that the clinician can see related to their wearable data. This is the data set that is exported. Some are normalized feature vectors, and some are not, like the weight. BMI is calculated, and so on. These are then uploaded through this system, and at the end we get the coaching. So in another tab in our system again, the coaching messages sent, the recommendations, let's say, sent to the patient. And on the right, you can see how these are received by the patient through the chatbot. And on the left, you can see the segmentation of the tips or the content related to, if it's related to physical activity, self-care, or per domain, let's say. So some identified risks are that, of course, the advice has to be should be regulated by an individual, by an HCP, to check that that there's no risk for the patient, and the HCPs always have to have the final say. But we want to focus on the benefits that patients can stay at home but receive a monitored treatment for lifestyle change, and healthcare professionals can benefit by offering such a personalized healthcare to the patients enhanced by these models for decisions. And the main aim for the healthcare organizations is to reduce the hospitalization time needed per patient and the risk identification earlier on, to reduce comorbidities and so on, and improve the health of the patients. That's it from my side.
Everyone, my name is Emiel. I'm from the University of Groningen. And together with my colleague Elisabeta, we will present some work on explainability and recommendations, and that is mostly linked to neurosymbolic learning. So, yeah, as we already saw in Spyros, is slides that many AI systems like neural networks, they operate as black boxes, which is problematic in some decision cases like healthcare. And also the current existing explanation methods that are applied after model training, they have some limitations. So they may approximate model behavior, but they may not reflect the actual decision process of the model, or even lack causal grounding. And this also results in users that may misinterpret explanations, and which could also lead to trust wrongly placed in the wrong systems, let's say. So with neurosymbolic learning, we try to combine symbolic methods and subsymbolic methods, for example, neural networks, to improve both model performance, so the outcomes of the model, but also the interpretability. And if I want to highlight a few observations from the HumAIne project. And first, that is, of course, if we have a neurosymbolic system that has a separate symbolic and a separate neural network, then we achieve transparency partly by design, because the symbolic part remains directly interpretable. So, the symbolic component might act as a reasoning layer that can be understood by a human. But of course, it becomes more challenging when we try to integrate them. For example, what we do in logic tensor networks, when we try to train a neural network and also satisfy for knowledge satisfaction, then the knowledge becomes embedded in the network, let's say, and the rules might be satisfied to some degree, but they are possibly not completely satisfied. So that results in new challenges that should be solved. But of course, this also enables layered explanation. So as Spyros showed, we can, for example, use the feature importance scores to explain the neural network, and on top of that, use some rule-based explanations to show why a particular recommendation was generated. And another observation is that the use of neurosymbolic AI also requires some new structures from an organizational perspective. So we need collaboration between the experts, in this case, the healthcare professionals and the AI engineers. So in the first place, the healthcare professionals would need to declare their domain knowledge, and the AI engineers should make sure that he understands it and he translates it in the right way into the network so that the meaning is also preserved of the domain knowledge. But also over time, of course, if domain knowledge changes or should be updated, then also processes should be in place that facilitate these updates. And beside this, it's also important to think about the stakeholders. So explanations can be given to the AI engineer during model development, but this person might need a different explanation than the final end user, for example, the doctor, that might require simpler explanations. And we have a few challenges. So as I said, the explanation quality depends on the accuracy and the completeness of the encoded knowledge. It is easy to miss knowledge, and that's also becoming problematic when we try to provide explanations. And of course, ensuring the accuracy of the knowledge base over time. And the third one is that soft constraints mean rules might not always be fully satisfied, as opposed to hard constraints. And the fourth observation before I give the floor to Elisabeta is that there's, of course, the introduction of LLMs. And in the HumAIne, we also try to put LLMs to work in this process. And in the literature, there's a growing attention to knowledge representation methods, for example, knowledge graphs or ontologies. And these can, of course, support NeuroSymbolic AI. And in this process, large language models may assist with, for example, extracting rules from documents or translating domain knowledge into machine-readable formats, for example, logic, or generating an explanation for stakeholders. And this can, of course, provide new ways to achieve trustworthy AI. And now I will provide the floor to Elisabeta, who will provide one specific example of how we can use LLMs together with NeuroSymbolic AI.
Thank you, Emiel. So next, I will again focus on healthcare. So building also on what Emiel explained, we often see promises of AI in healthcare and also in other domains, such as better and faster care, personalized medicine, predictive analytics. And the promise is there. We see almost 8% of healthcare professionals are optimistic that AI could improve patient outcomes. However, the reality is a bit more nuanced. We see, as Emiel mentioned, black box models, hallucinations, errors, and essentially the results, as the Future Health Index 2025 by Philips reported, is that only 38% of clinicians believe that these tools meet real-world needs. So to bridge the gap, NeuroSymbolic AI can be paired with knowledge graphs, RAG, and also powered by LLMs. So the example I will talk about, let's go a bit in the architecture. Essentially, we have the knowledge graph, which is the structured human readable knowledge. Essentially, we have information in the form of triples, and the knowledge is directed and connected. The NeuroSymbolic AI, again, we are using logic tensor networks, which uses embeddings and rules that influence recommendations. GraphRag, which uses vector similarity, keyword matching, but also graph traversal to get the hierarchical information in the knowledge graph. And again, powered with LLMs to the generative power for human readable outputs. And also what makes this, this solution a bit different is that we can output the references from the knowledge graph and the NeuroSymbolic AI, and we ask the LLM to make sure that these references exist in those two, and also, if desirable, to output them so the outputs can be traceable, can be transparent, but also auditable. So AI essentially thinks more like a doctor, and it can explain its reasoning. So going a bit in the workflow, we see that the user enters a query, the retriever does a hybrid cipher query, which is the vector similarity, also the full text search, and then the retrieved results from the offline trained, they get a confidence that they are the fuzzy logic, also as Spyros mentioned, that we can output them. The offline trained LTN uses the knowledge graph triples and also the AMI rules. So AMI rules are essentially mind rules from the knowledge graph. It uses the statistical patterns of the knowledge graph, but it can also, we can use rules from clinicians, which might be actually more correct in that sense. So next, in the augment part, in the prompt construction, we essentially put together the user query, the retrieved knowledge, and the instructions. And then in the LLM, we give those information. It's with the instruction we have provided it, it creates an output, and then the citation verifies everything. Here we can see also an example, input and output. I'm not going to get into the information, but essentially we can see that the output is structured in a way that clinicians can also skim it, but also go into more detail if they desire. Into this blue brackets, we can see the facts from the knowledge graph, but also the LTN. And also in the lower part, we can see the evidence summary, how many graph facts have been retrieved, how many have been validated by the LTN, but also the confidence range. So essentially, I would like to focus that NeuroSymbolic AI is domain agnostic. It can be applied whenever high stakes decisions are needed, complex rules, constraints. It can be used in example domains such as manufacturing, finance, smart cities, energy, and so on. But also, it's not only about recommendations. It can be used for verification, policy validation, and so many other examples. And essentially, the key takeaway is that NeuroSymbolic AI integrates elements that can contribute to the development and trustworthiness of AI systems, particularly in high-stakes decisions. Thank you.